Have you ever noticed how many systems in our world seem to just know how to stay on track, whether it is maintaining a comfortable room temperature or keeping a car at a constant speed? This remarkable ability to self-regulate is often due to a fundamental concept in engineering and nature. A negative feedback loop operates as a self-correcting mechanism where a system's output is measured and then fed back into its input in an opposing way. Essentially, it works to minimize the difference between a desired state and the actual current state, continuously making adjustments to achieve and maintain stability. The core reason this works so effectively lies in its error-reducing nature. In a typical negative feedback system, a sensor measures the actual output. This measurement is then compared to a reference input, which represents the desired output. The difference between these two values generates an error signal. This error signal then drives a controller, which in turn adjusts the system's input to counteract the error. For instance, if a system's output is too high, the negative feedback loop will generate an error signal that causes the input to decrease, bringing the output back down toward the desired set point. To put this into practice, consider how a thermostat in your home uses negative feedback. You set a desired temperature, which is the reference input. A temperature sensor measures the actual room temperature, the system's output. If the room temperature falls below your setting, an error signal is generated, telling the furnace to turn on and add heat. Once the temperature reaches or slightly exceeds the desired level, the error signal changes, and the furnace turns off. This continuous cycle of sensing, comparing, and adjusting ensures the room temperature stays within a narrow, comfortable range. Beyond simple thermostats, negative feedback is the backbone of most precise control systems. It significantly enhances stability, reduces sensitivity to external disturbances, and improves the overall accuracy of a system. This elegant principle allows for a high degree of system robustness, meaning the system can maintain its desired performance despite variations in its internal components or environmental changes. Understanding this principle is crucial for designing everything from automated industrial processes to sophisticated electronic circuits and even biological regulatory pathways. In essence, the operation of a negative feedback loop is about achieving stability and precision by constantly monitoring and correcting deviations from a target. It transforms an open-loop system, which is prone to drift and error, into a much more reliable and predictable closed-loop system. This foundational concept underpins countless modern technologies and natural phenomena, allowing complex systems to function smoothly and efficiently by continuously striving for their desired state.